Hi, in this sequence of videos we're going to be looking at these little puppies, capacitors. Now they are simple devices, they store charge and they store energy. We're going to be looking at what they are and how they are made first of all. We're going to be looking at how they store energy, and we're going to be looking at how they discharge that energy and that charge so that basically you can pass your A-level exam with flying colours. Let's get started. So, what do capacitors do? Well, let's show you. First thing I'm going to do is basically get you to look at this simple circuit. It's basically 3 cells and a voltmeter. And when I plug my voltmeter into the cells of the batteries, I get the voltage, 5.5 volts roughly. So when I pull it off, break the circuit, it goes back to 0. Plug it in, 5.47, pull it out, goes back to 0. Now what you should be noticing here is how quickly it goes back to 0, which is pretty. It's not completely instantaneous, but it's quite close to being instantaneous. What happens now? We're going to make a simple capacitor. So, got myself a big piece of silver foil, and I've got myself a roll of cling film, available in all good kitchens. Now, I'm going to very carefully cover over the cling film, cover over the silver foil, so that it is completely covered by the cling. It's overlapping all the edges, as you can see here. And then I'm going to stick a crocodile clip onto that piece and make sure that it's properly insulated. There we go, like so. Bish bash bosh. Next up, I'm going to get myself another piece of cling film, silver foil, place that down on top of the first one. So the 2 pieces of silver foil are separated by the cling film, and that's the crucial thing to be aware of. This it's just 2 simple conducting plates, 2 bits of foil separated by an insulator. Now if you've already studied fields, you'll know that if I apply a potential difference across the 2 plates, I will get a field between them. So I'm going to plug this into here and plug this into there. First thing you notice, no difference to potential, because fundamentally 2 bits of silver foil don't actually generate any sort of potential at all. They don't really do anything, they're just sitting there carrying a bit of charge from the cells. I'm going to get my hat and wipe it down, basically get them nice and close to each other so that I've got no air in between the 2 plates, in between 2 bits of foil. And now I'm going to break exactly as I did before. I'm going to pull this down so you can see it. I'm going to break the circuit and we're going to see how long this takes to go back to 0. Now it's not going to take much longer, but you can see it does go down slowly. Now what this is showing us, you can see it's still going down, 0.02, 0.01, and it's finally back to 0 there. So what this is showing us is that the potential difference from the 2 ends of these cells shared. This end is at high potential, this end will be high potential, which is connected to the bottom plate. And this end is at 0 potential, connected to the top plate. And the potential difference is shared across these plates here, these pieces of foil. And therefore, what it's doing is it's pushing some charge onto these 2 bits of foil. And when I break the circuit, you'll see that charge is leaking away. But the key crucial thing is, for bit anyway, it is holding and storing some charge. And that is all that a capacitor is. It's something that stores and holds charge. Let's take a look in more detail at why they're so useful, or what they do really, and what we use them for. So what have we just seen? Well, as we saw when we attached the capacitor to the cells, when we broke the circuit, we saw that the potential difference stuck around i.e. there is some charge being stored in the capacitor. Now, how does it work? Basically, the cell's a source of EMF. It wants to drive electrons from the negative side around the circuit, and of course these electrons are going to build up on one of the pieces of tin foil. Okay, now because the electrons are negative, we could say there's a net build up of charge, Q. Now of course it's a negative charge because electrons are negative. I'm going to put my Q a bit better. Because electrons are negative, we can say there's minus Q charge is built up on that plate. Obviously, because electrons are negative, they're going to repel electrons in the other plate. They're so close together, the electric field from these electrons has an action or an influence on the other plate, and so the electrons over here are going to chip off. They're going to go around to the cell, and so we're going to get basically an absence of electrons over here, and therefore a net positive charge building up on that plate over there. And we say, therefore, negative Q's built to one plate plus Q's built to another plate. Essentially, charge Q's gone in and charge Q's come out. So we can say the build up of charge is Q. Now, it stands to reason that the stronger the cell, or the greater the potential difference across the cells, the more it's going to push electrons around. And so what will always happen is, whenever you put a PDV across a capacitor, it's going to build up a charge. Now it just so happens that it can be shown by applying a constant current into a capacitor, but it's fiddly and I don't have the gear to do it. But if you did, then what you'd say is, as you increase, what you'd find is that as you increase the potential difference across the capacitor, the amount of charge in the capacitor goes up in a nice uniform manner, i.e. that's the straightest line I've ever drawn in my life. But i.e. if you double the potential difference, you will double the amount of charge stored in the capacitor. And the capacitor has the units of capacitance are the farad, but the relationship between Q and V is Q equals VC, which basically means C is the ratio of Q over V. Now I don't know why, if it helps, but for some reason I remember my physics teacher telling me Queen Victoria Cross, and I don't know why, it just always stayed in my head. I didn't even know what Queen Victoria Cross was at the time, but there you go. Q equals VC, that stuck in my brain, and that's what needs to stick in yours. Now the capacitance of a capacitor is the ratio of charge to voltage that it holds. Okay, so C equals Q over V, and it has the units of the farad. So to define the farad, well, the farad is the unit of capacitance that is equal to 1 coulomb of charge. A capacitor of 1 farad will hold 1 coulomb of charge when a potential difference of 1 volt is applied across the plate. Okay, now in reality, these things hold a 1 farad capacitor would be an absolute beast. By normal electronic standards, these things are pretty big. The things you're getting in most of your digital circuits are really icky bitty little things, but these ones are pretty huge, and these are 470 microfarads. Okay, so a typical capacitor is in the order of micro or nanofarads. Okay, so a farad is a pretty large unit of capacitance, but it's the unit that we have. So that's what's going on so far. If you put a potential difference across the plates, charge builds up. That's easy to understand. The greater the potential difference across the plates, the more charge there is that will build up on them. The ratio is constant, i.e. if you double the potential difference, you double the charge, and the capacitance of a capacitor is the ratio of charge to voltage. The formula that puts it all together, Queen Victoria Cross. That's all we really need to know about at this stage.